Okay, good morning, everyone. This is Randy at SSC. Thanks for joining the call today. We have a real pleasure in having Trevor Alcott joining it and presenting on Ensemble Post-Processing today. He works in the Model Development Branch at GSD in Boulder, or from her Post-Processing. He's one of the sharpest people in this agency and one of the sharpest people I've met anywhere, for that matter. He's got his PhD from the University of Utah. He did some outstanding research out there with Jim Steenberg on orographic influences on lake effect snow, also on Great Salt Lake LES, lake effect snow frequency characteristics and associated environmental factors. He's also done work on snow to liquid ratio variability in complex terrain, which led to a technique that's been utilized at many offices in the western United States. He's a real expert in ensemble output and the operational use of ensembles. The anomaly situational awareness table was really, the development of that was when Trevor and I were working in Salt Lake City when he was in graduate school and then his PhD work. In the past few years, he's been presenting on ensembles at the SOO development course. So many of you newer SOOs have seen him and speak there. So anyway, thanks, Trevor, for taking some time today to join us, and we'll just kick it right over to you for your presentation.
All right. Thanks, Randy, for the introduction and the kind words, and I appreciate you and Bruce inviting me to speak to everyone. First of all, a quick aside here. This is a screenshot from a webcam the other day in the Colorado Springs area, and this is one of those unique areas in Central Region where complex terrain coincides with severe convection. So it's kind of as hard as it gets when it comes to high-resolution model prediction. Sorry, taking me a second to advance. There we go. Just a few things I'm going to be going through. Can't really talk about post-processing until we talk about some of the operational ensembles we're running in the first place, and how we evaluate them to know what degree of post-processing we want. So I go through running ensembles, evaluating some of the post-processing techniques out there, and some of the post-process products that you can use today, some that are on the way pretty soon. So first of all, this is the most common type of ensemble that you're going to see in operations. It's the only one that's in official NCEP operations. It's the mixed physics or poor man's ensemble. And really they're essentially the same thing. Poor man's ensemble, taking advantage of various deterministic model systems that are lumped together, versus a mixed physics ensemble like the SREF, which is kind of intentionally put together from one starting point, but all the same type of perturbations. So we're starting off with these various initial states. We're using often different dynamic cores, different model physics, and all your spread is coming largely from systematic biases in the various ensemble members. It's not coming from just random perturbations. So the concept is we're combining multiple deterministic models, utilizing systematic and non-systematic biases of the individual members to create spread. The strengths, this is really inexpensive. All these deterministic models are already running. So as far as href goes, there's some fairly simple code to just lump all that output together and produce some probabilities. The other strength is that there's actually quite a bit of spread in this system, the href in particular, and it is tough to beat right now. I'll go through some verification, but we're at a point where the latest and greatest initial condition ensembles can't quite beat the performance of the href. Again, sorry about the background noise. I'm not sure if you can hear the vibration of the vacuum outside, but hopefully it'll be over in a minute. The weaknesses of this system, well, the problem is when your spread is totally based on just systematic biases in the model, it's not rooted in the actual sources of uncertainty. So in theory, we want all of our members to be equally likely. We want them to start from equally likely initial states, and we want all of either one set of physics, or we want all these various types of physical parameterizations to be equally plausible. And that's not really the case with what we're working with right now. The other thing that comes out, and especially on the post-processing side, is that bias correction will decrease spread, because if your spread comes from systematic biases, and you decrease your systematic biases, you decrease your spread too. On those same lines, if you improve the models, you decrease your spread. So the kind of limit as time goes to infinity of the href is a deterministic model. And again, each member is not equally likely, so we do end up with reasonably good spread and reliability, but not quite as good as you would be with an ideal system that is completely random. And the other thing, it's complex to maintain. So href as it stands now is 8 members. It's really 4 members plus 12-hour-old versions of those same 4 members. So you're dealing with 4 different systems. You're not just maintaining one set of physics, one dynamic core. You know, any upgrades are going to be on 4 individual components. You know, there's a lot of bookkeeping with that, both on the computational side and on the kind of implementation side at NCEP. So if you were going to do this from scratch and you had the resources for something better, you would want to do something better than that. It's a little bit on the short-sighted side, but you know, it's really working with what we had when we had it. Time-lagged ensembles. A lot of people are probably familiar with the Her time-lagged ensemble. And I have to clarify that this isn't something that we've been trying to get into operations. You may see some kind of time-lagged component in the future of high-resolution ensemble systems just because it's cheap. But really the purpose of this system, we just wanted some ensemble members to work with to develop post-processing. So we just wanted something there to see if we could add value with bias correction and increasing spread. There are some examples of this out there in operations. Actually, the climate forecast system, the CFS, is a time lag system. They run a model every 6 hours, and they're lumping together those outputs many weeks out in time. The hurdle itself was 3 members. We're still keeping it running, just again to experiment with post-processing, but I think with a lot more effort going into her ensemble, I think we're probably going to see this die out in the next year or two. Kind of served its purpose. I mean, the strength here, much like mixed physics or poor man's ensemble, it's really inexpensive. Frequent updates, because the model's running every hour, you can come up with a new ensemble every hour. Biggest weakness is that these systems are really under-dispersive. And the differences between models initialized at, say, 20, 21Z, 22Z are really not, those differences are not as large as the real uncertainty in initial conditions. And your older runs are going to become progressively less skillful. So this idea of an ideal ensemble where every member is equally likely, well, the older members are less and less likely to be correct. So it's not an ideal way to construct a system. And typically, we found once you went back more than 6 to 8 hours, you really weren't adding a lot of value with older runs. I think the differences with something like href, where you have models that are cold started, so they require some spin up time, that's a case where your older runs may have equal or even better skills sometimes than your newer runs. But with a hourly initialized full data assimilation system, you can't go back very far and still get value in a time-lagged ensemble. It's also a tough balance between forecast length and membership size, right? Because if you keep going to older and older runs, your forecast horizon comes further and further back. So if you have if you have a deterministic model that runs out to 15 hours, okay, if you want 3 members, you can get a 13-hour forecast. But if you want 10 members, you're going to get a 6-hour forecast. So there's a real trade-off that happens there. But again, the biggest advantage to this is, well, we're already running the model, so you might as well lump together a bunch of runs and see if we can get any useful uncertainty information. Just showing a quick example of a HER time-lagged ensemble, and this kind of showcases a lot of the issues. I mean, the obvious advantage here, if we look at our 1, 2, and 3-hour forecasts from different initialization times on the right, you do see some spread. You kind of get a little sense of the uncertainty, but you also notice, well, none of them are right. So you get spread, but none of them actually capture what happens in the 2Z MRMS analysis on the left. So when we start to talk about more sophisticated systems, let's look at initial condition ensembles. Examples right now would be the HER and the NCAR ensemble. I think a lot of people really liked looking at the NCAR ensemble, which it's gone to more of a in the background research state than a real-time system that's shared with everybody. HER is still running twice a day, but neither of these systems are on a direct track to operations. These are both R&D systems, and we're working pretty closely with NCAR, where we try to have essentially the same system, but just 1 or 2 specific differences, so we can evaluate, okay, is it better to run a system this way, or is it better to run a system that way? Once we establish that, we move on and we test a different difference between the 2 models. So this is kind of your simplest full ensemble, where you have random perturbations to the initial states, but you run 1 set of physics, 1 dynamic core, basically running the same model multiple times. In the case of the HER and the NCAR ensemble, 9 and in the past 10 times respectively. So there's real advantages here from a programmatic standpoint. You're only working with 1 modeling system. The disadvantage is, unlike a time-lagged ensemble, you have to initialize all these members at the same time and run them all at the same time. So it takes a lot of resources to be able to do that. And I think in reality, you're going to end up with a system like this in operations probably in the next 4 to 5 years, but it's not going to be running every hour. You're probably looking at something like a once every 6 to 12 hour initialization, just because it is so expensive to do this. And that being the biggest weakness. Now the other weakness, and I'm not sure how much this gets talked about, is that most of these systems are still under-dispersive, so failing to represent the full range of possibilities. And the first iterations of both the HER and the NCAR ensemble still aren't as reliable as the HREF. That kind of leads into the next type of ensemble system. And this is it's really an add-on to an initial condition ensemble. So we're starting with various initial states, but along the way, we're perturbing the physics. And there's a lot of different ways to do that. One is just perturbing some of the constants. So say there's some constant 0.6 that's involved in conversion of cloud droplets into rain. Well, we might run the system once at 0.5, once at 0.6, once at 0.7. So there's one way is just perturbing parameters of the physical parameterizations. Another way is perturbing the physical tendencies. This is this SPPT, Stochastic Physics. I'm missing what the second P is in there, but that's the physics tendencies perturbations. And what we've found is by doing this, you're certainly able to get more spread, because if you assume that all of the uncertainty is just in the initial state, you're never going to end up with a wide enough range of possible solutions, because none of these systems are perfect. None of the physics are perfect. But since we don't know what the absolute perfect physics package is, we need to allow for some range of model uncertainty. And applying these stochastic physics techniques does provide you with additional spread. This is very experimental, and honestly, despite the fact it's been around for 10 years, it's somewhat in its infancy. Stochastic physics is being used on the global scale. I'm not sure if it's in the operational GEFs now, but it's certainly in the experimental. So it has a little bit better track record on the global scale, but on in regional models, high resolution, this isn't being, we're not getting as much spread out of this as we would like yet, but there's a lot of potential here. Another aspect of this is actually perturbing the soil moisture at the beginning of the run. So that's another place where there's a lot of uncertainty. And it's not handled by one system that just takes a single soil state and runs with it. So all of this is trying to target the real sources of uncertainty rather than just taking whatever deterministic models are out there. So we don't know the exact state of the initial atmosphere, and we don't know what is the perfect set of physics. So that's kind of what we have to work with right now. I think we have a joint project with NCEP right now, between Esrel and NCEP, and also OU, where we're trying to figure out, okay, what is the best path forward for a single core ensemble system, that core being FV3. And we're all kind of working together to try to at least equal the performance, or hopefully exceed the performance of our current mixed physics kind of poor man's ensembles. So there is an agreed upon path forward, and we're not kind of just off doing our own thing anymore. So I'm not sure the exact timeline for this, but we are moving towards a coherent single core system that will take advantage of stochastic physics. So when it comes to post-processing and really ensemble output in general, the only way for a probabilistic forecast to be useful is for it to be relevant to decision making, for one thing. That PDF needs to be sharp enough to actually make decisions. If it's not, I mean, it might as well be climatology. And it needs to be reliable enough that those are good decisions. So I'm really focusing on the sharpness and reliability aspects there. And the way we evaluate that, there's kind of the most basic way is with these rank histograms. And I think a lot of people have probably seen this before. Say you have a 9-member ensemble here, and if it were performing well, all those members would be equally likely. So verifying in any of those 10 bins, including outside of the members, should be equally likely as well. So you should have a 10% chance of verifying between member 1 and 2, just the same as 4 and 5. And if you look on the outside, with a 9-member ensemble, there's a 20% chance that you verify completely outside the envelope. And I know we don't like that in operations, and it makes the statistician a lot happier than it makes an operational forecaster, which makes a lot of sense. It is okay to verify outside the envelope from a statistical standpoint, and it should happen roughly 2 over n plus 1 times. So 20% of the time for a 9-member ensemble. So kind of how we look at these rank histograms, you can pick out on negative and positive biases. Ideally, you want kind of this flat, consistent relationship in the center. But what you see way more common in any of the operational systems, and especially with time-lagged ensembles and with kind of the first iteration of initial condition ensembles, is the bottom left, this under-dispersive forecast, where way too often you verify completely outside the envelope. Statistically, part of that time you should end up around that 10% line, but you know, a lot of these systems you're verifying outside the envelope almost half the time. So the purpose of post-processing is trying to make up for the inability of a raw ensemble forecast to correctly estimate the full range of possibilities. So the other thing we're going to look at a lot are reliability diagrams, and I think probably every SOO is going to be familiar with these just from evaluating POP forecasts. And we're trying to achieve our perfect reliability here, where your probability is equal to your observed frequency. So 30% of your 30% probability forecast should verify. A lot of the time we see under-dispersive forecasts. This is how they look from an ensemble system. So just showing overconfidence. You know, your 0% forecast verify some of the time, maybe 15% of the time, and your 100% forecast might only verify 60% of the time. Occasionally we'll get over-dispersive systems. This is the only place I've seen this in operations is with the SREF. I know if anybody's looked at SREF snowfall forecasts, you see a lot of these 0 to 50 inches possibilities, and you're really going to end up along those yellow lines. So for some of these SREF forecasts of 60% chance of 12 inches of snow, well, that might really be 100% chance. But far more often with our high resolution systems, you're going to see under-dispersive forecasts, just this classic red line where you're overconfident on both ends of the scale. Nothing's going to happen. Well, it does sometimes. This is definitely going to happen. Well, a lot of the time it doesn't. So the purpose of our post-processing is to try to address that. So I've split bias correction and spread augmentation up. Those can be done individually or together, and I'm going to show examples of both. First of all, with bias correction, this is something we did with the HER time-lagged ensemble, and we're going to be implementing it in the HREF this fall. And what we're doing is just showing an example of current biases in the top left here. We've seen an improvement in the high QPF bias in the HER over the last few years. It's certainly a lot better than we were in 2013, but there's still a lot of these instances where this is a frequency bias here. So anywhere where you're above 1 for these various thresholds, it means that the model is forecasting you to exceed 2, 3, 4 inches of rain much more often than it actually happens. And we really want to get that down to a 1. I mean, we want the model to forecast events as often as they occur. And over a series of experiments, we found that what we can do is this quantile mapping bias correction, where we say, let's look at the 99th percentile QPF in the HER, 99th percentile stage 4 QPE. And we come up with a linear correction. So say the 99th percentile QPF is 2 inches, and the 99th percentile QPE is 1.5 inches. So this is saying that the model has an over-forecasting bias. What we do is we come up with a correction where we adjust that 2-inch QPF down to 1.5. And that's done for all of these thresholds from 1/100 of an inch up to 3 to 4 inches in 6 hours. And we find that if you look at the U.S. as a whole, or at least split it up into fairly large regions, you can lump together all these grid points. You're not doing this at grid point by grid point. We're saying let's lump together all of the point forecasts over a large region from only, say, the last 50 forecast QPF pairs. And we're able to get pretty close to a neutral bias using just the last 50 pairs of QPF and QPE. When you get to more and more forecasts, what you're doing is you're actually getting into a different season, so the correction can be a little bit different. If you have too few, you're going to have a poorly conditioned curve fit. So there's a balance right about 50 forecasts we found. So we're applying that bias correction in the HER time-lagged ensemble, and again, that will be implemented in href this fall. And the way that works, it needs to be done separately for different lead times and different models. So if you have an initial condition ensemble, it's pretty easy. You're only applying bias correction to one system, just a control member, because there's no systematic differences between members. But with a system like href, you need to come up with a bias correction curve for each component. So it's a little more complicated, but Ben Blake at EMC was able to sort that out from our code, and it's going to be applied correctly in href. Another type of post-processing that becomes necessary is spread augmentation, so increasing spread. And just showing an example on the right, one of the simplest forms is to just calculate a straight relative frequency of exceedance across all the members and then run a Gaussian smoother. That's really the most basic form. And that, for a loss in sharpness, it will help you to increase reliability. There's always going to be a trade-off there when all you're doing is just doing a spatial smoother. Another type is some of these other spatial filtering approaches. So this is what we did in the HER time-lagged ensemble. And a disadvantage to just smoothing the probabilities is, say you only have 3 or 4 members. So with 3 members, you only have a possibility of 0, 33, 67, or 100% chance of exceedance. And if you run a smoother on that, it's still not going to look very good. You're not going to have much resolution. So what we did with the HER time-lagged ensemble when we only had 3 members is we said, well, let's look in a circle around a point. And let's say that the forecasts within 40 kilometers of that point are all equally likely solutions for the forecast at that point. So you're kind of saying, well, let's look at all the points in 40 kilometers and call them members. And with a 40-kilometer radius, you end up with over 500 grid points. With 3 runs, you're essentially looking at 1,600 ensemble members. So what you've done is really increase your ensemble membership and increase your spread. If you do this in each ensemble member, you're looking at what fraction of those members exceed a threshold. So you can come up with, say, this example here is a very crude one, but in member 1, 48% of the so-called ensemble members in that circle exceed a threshold. Member 2 might be higher, member 3. We just take the average of those fractions of exceedance. So it's called a fractional coverage approach. Filter doesn't have to be circular, but we've been going with that for now, just for simplicity's sake. This does improve your reliability, but of course at the expense of sharpness. The other thing is that we don't have to use a fixed radius everywhere in the entire domain, and I'm going to show an example of that in just a moment. Just showing some of the impact here. So on the left you have, in the reliability diagrams on the left, you have reliability of 0.01 inch forecast within 40 kilometers. So you're looking at various amounts of smoothing here. With no smoothing, that's your solid blue line. It's your classic underdispersive forecast. So your 80% chance of exceedance only verifies 40% of the time. But if you run a wide Gaussian smoother with 120 kilometer radius, your reliability, it's not perfect, but it does get a lot better. That's that small dotted line. And the same thing on the right for half inch, and the same amounts of smoothing. But one thing you'll notice in the histograms in the bottom is, I suppose this is somewhat intuitive, but if you do too much smoothing, suddenly you don't get many 100% forecasts anymore. So all these really isolated points get smoothed out so that a lot of your 100% forecasts are probably down in the 60% range. So that's your loss of sharpness. But again, it comes with an increase in reliability. Again, you do have to be careful with that, because if you do too much smoothing, eventually you're just ending up with climatology. And there's very little skill in climatology. I would say the value of the expert is on what you can add over climatology, because anyone could just look that up. Just showing some examples of where Gaussian smoother is used. What we've been doing is very similar to what SBC is doing to help with their forecasts. We've been taking ensemble forecasts, in this case the Hurry, and looking for to forecast hail and severe weather, looking for exceedance of updraft helicity greater than 75, as well as some other severe weather parameters. And we find, based off some research that was done at NCAR, Ryan Sobash and Craig Schwartz, that a Gaussian smoother of width 120 kilometers gives you forecasts that are kind of on a similar scale to what SBC is doing, and with similar reliability. So this is an example of our 4-hour probability of hail and tornado and the one-day SBC forecast. So kind of mixing lead times in here a little bit, but giving you a rough idea that with an appropriate Gaussian smoother, you can get a similar looking probabilistic forecast. Another thing we don't talk about too much is a certain amount of smoothing is necessary just to improve resolution. And by that I mean resolution in the probabilistic sense. So if you have 3 members here and they're all showing convection in different places across the state, you would think that your probability of a thunderstorm at this blue dot is definitely not 0, because there's a certain amount of possibility that convection could form in between members 2 and 3. If you don't do any smoothing, you would get a probability of 0 right there. So a certain amount of smoothing or spatial filtering is necessary just to deal with this situation. The other possibility is to just keep adding members until you fill in that PDF, but I think you'll find that smoothing is a lot cheaper than running a really huge ensemble system. Last component of post-processing is providing context. And I think this might be a no-brainer for some folks. It's really just kind of addressing the DSS side of things. So we don't just want to know, okay, what's the probability of 1 inch of rain, but what's the probability of exceeding flash flood guidance? What's the probability of exceeding a recurrence interval of 25, 50, 100 years? What's the probability of heavy rain on saturated soil? And another piece of this would be joint probabilities. So looking at, say, blizzard conditions, what's your chance of exceeding 35 mile per hour wind gusts, low visibility, and so on. One other aspect to this, this is not going to be part of what's going into HREF right now, but there's much more advanced ways of post-processing where you deal with bias correction and increasing spread at the same time. And this is some work that's been applied to the GAFS ensemble by Michael Schroeder and Tom Hamill. And what they're doing is, by looking at a long period of matched ensemble forecasts and QPE, they come up with a parameter correction where they take the ensemble PDF in real time and they adjust both the mean and the spread at the same time. And they're doing these gamma curve fits. So you have two parameters of the gamma distribution. You also have a shift, and then you have a cutoff at 0 because you wouldn't want a probability of -1 inches of QPF. So this is called a censored shifted gamma distribution. Censoring meaning less than 0, and shifting meaning literally just shifting along the x-axis. So they're using the ensemble PDF, applying some parametric method to predict what the real PDF should be. Now this is a little more complicated to do with high resolution models, any kind of short intervals, because you have a lot of areas where nothing is predicted, like that last example. So that's probably a case where if we wanted to look at a parametric correction like this, we would want to not just look at the forecast at a single point, but again be looking at some radius around that point and say, well, these are members that we could lump into the PDF before we apply any kind of correction. And on the bottom right here, you can see that they get a pretty darn good reliability out of a correction like this on the global ensembles. So when we look at what's going into HREF, we got multiple approaches here. First of all, that quantile mapping bias correction on the QPF. Again, with HREF, you have different ensemble systems, so you have to apply this separately to the ARW and the NMM components. Then we have kind of these neighborhood methods where we're increasing the spread in the ensemble system. Spatial filtering is used in the HREF. I think you might see Gaussian smoothers used in the future where we have enough members we don't need to kind of inflate the membership as much. Just showing some of the output from that. This is kind of, I don't want to start a ESRL versus NCEP war here, but this is kind of where we stand with hurry relative to HREF. You can see the bias characteristics are quite a bit different, but I really want you to focus on the reliability diagrams in the top right. And you can see that even when we apply smoothing, and that'll be the dashed lines there, you don't do as well with reliability from the hurry as we do with the HREF. It's apparent with low thresholds of, say, 0.01 and also with 0.05, although I do want to say that even with post-processing, the reliability of heavier rainfall rates is still not very good. We still have some under-dispersion problems. So a lot of work to be done there. Same thing for 18 to 24 hours. You can see we do a little bit better. Under dispersion with pretty much any system is at its worst in the first hours of the forecast. The spread just doesn't grow as quickly as it should. But you'll see at this 18 to 24 hour lead time, especially for the half-inch threshold, there's a pretty significant improvement in reliability when that spread does start to grow. So one last component of the href post-processing I want to talk about is this idea of ensemble agreement scales. And this is a technique that came out of the UK Met Office. A lot of what I talked about and a lot of what's been done on the hurdle is using a fixed radius and saying, okay, the ensemble does not have enough spread, so let's apply this spatial filtering approach with, say, an 80-kilometer filter in every situation at every grid point, no matter what. And there's a lot of cases where that doesn't make sense. The most obvious one being in complex terrain, where in theory you could be using this point way out in a valley as an equally plausible solution for a probabilistic forecast in the mountains. And that just doesn't make sense. So what we want to do is, we know that the model doesn't have enough spread, but we also know that there's at least some value in the spread-skill relationship. So our goal is, we want to look for situations where the ensemble members are in pretty good agreement and not do as much smoothing in those areas. So the way ensemble agreement scales works is, well, let's see over what kind of scale do the ensemble members agree. So let's look over a progressively larger radii until we get very similar forecasts. And that's judged by, okay, what fraction of the members exceed a threshold. So in figure A on the left, you wouldn't have to go to a very large radius before you'd find that essentially all the members agree on the same solution. Whereas in C, you need to be at a fairly large radius before you're getting the same message from all the members. So the idea is that you do relatively little smoothing with A, a little more with B, and a lot more smoothing with C. The kind of physical analogs for these, A would be like an orographic precip scenario, where there's fairly high confidence. Precipitation is going to be mostly confined to a narrow area over the higher peaks. And C would be more of your kind of scattered plains convection scenario. And that's where you really want to do a lot of smoothing there, because there's not only a lot of uncertainty, but there's a lot of areas where ensemble members might not have any precipitation, just because there aren't enough members. So we've worked together with Ben Blake at EMC to get this put together for the href. And he's got a comparison here. Here's your straight point probability in the top left. This is just if you took, okay, what fraction of members exceed the threshold at this one point. On the top right, this is where we apply just one smoothing radius over the entire domain. And you can see where that really fails over the Sierra Nevada ranges. Bottom left, this is what happens when we apply an ensemble agreement scales technique. And you can really see how the probabilities are a lot higher over the Sierra Nevada. So we're not adding as much smoothing in these areas where the ensemble members agree on heavier precipitation. And in the bottom right, you can see the radii that were used to do that smoothing. So in a lot of areas where you have scattered convection, you can see the dark red 100-kilometer smoothing. And over the high terrain, you can see as low as 10-kilometer smoothing. And so this is where we want to add variable amounts of spread to the ensemble forecast. We trust the spread-skill relationship, we just don't think the spread is big enough. Showing the improvement there, it's really most significant in the West because these complex terrain scenarios are kind of dominating everything. You can see the fractional coverage approach, that's the single radius in red, actually is kind of over dispersive. And what it means is it could be a lot more confident over complex terrain if we processed it correctly. And with the EAS, you get almost perfect reliability by doing just that. That's for ½ inch in 6 hours, and on this slide, 1 inch in 6 hours. and you can see that's even more pronounced, although we're not quite at perfect reliability. So lastly, I just want to go through operational products. First of all, things you can use right now. href version 2 does not have any bias correction. All it is a fraction of members that exceed a various threshold, and then 25 kilometer Gaussian smoother run on that. It's only point probabilities. As far as options for viewing it, the SPC has a web viewer that's pretty good for this. Still canned regions. I think we're probably a little ways away from a nice viewer where you can zoom in real time. Another option is to just pull the GRIB2 files directly from Nomad's FTP. And I know this is, I've been involved with WFOs and worked at a region, so I know how annoying this is that this stuff is not set up in AWIPS. And I think the best option for this to get this in front of people sooner rather than later is going to be through WAVE. So we're going to be working with those folks to get href products showing up in WAVE as soon as possible. The version 2.1 products, I have it here at fall 2018. I don't have a specific date for that, but I'll try to get the word out when we do have one. We're going to be doing the quantile mapping bias correction for QPF, this ensemble agreement scales approach, the variable radius filtering for both QPF and SNO. The plan is to have both point and neighborhood probabilities. And again, this is not about smoothing, this point versus neighborhood. It's about the product definition. So do you want to know the chance of an event at this point, or do I want to know the chance of an event occurring anywhere within 40 kilometers around the point? And they have their various uses for sure. Point probabilities we'd use a lot more for QPF, say in snow and complex terrain, but neighborhood probabilities more for like lake effect snow, really heavy rainfall rates over flat terrain. You know, we might want to know, okay, the probability at this specific point is probably pretty low, but what's the chance that we get some really heavy rates in this area? So we want to have both of those options available for people. And we do want to try to get this into WAVE. A lot of the people who work on WAVE are just down the hall, so this is a very easy thing for us to coordinate. Certainly something we're going to get going within the next year or two. Planned upgrades. A little funding's been thrown around to get some of these external data sets involved, so that we could have comparisons of flash flood guidance and return intervals. And I think there's a lot of options for fire weather there too. So we could look at, okay, what are our chances of low RH, strong winds occurring over areas where the fuels are cured. And also we want to get into some combined probabilities like blizzard conditions or your RH and wind for fire weather. I'm going to stop there. Sorry, ran about 10 minutes over there, but hopefully you got time for a few questions.
Thanks, Trevor. Awesome presentation. I think you touched on so many things that are really key, to the future of our agency. The ability to post-process effectively is really key to our decision support. And I think that some of the stuff you're talking about here is just so critical for us as forecasters to understand the difference between point and neighborhood probabilities, and then be able to communicate that effectively to decision makers. Great stuff. I'll open it up for questions. It looks like we have Matt Bunkers. I'm going to unmute you. Go ahead, Matt.
Yeah, I have a couple questions for you, Trevor. The first one, you'd mentioned that the time-lagged ensemble, the value of the past runs after about 6 to 8 hours falls off. But I was wondering if anybody's considered looking at trends of the ensembles. For example, the the QPF is increasing, or the convection's getting more intense, or the winds are either increasing or decreasing. So as a way kind of to leverage those trends, especially if it's consistent, not flip-flopping, but consistent. Is that something anybody's looked at?
So I tend to be kind of anti-trend. I think there is some information you can pull out of there. If you do see multiple runs showing the same thing, I look at that as increasing confidence. You know, essentially no matter what you do to the initial conditions, you get the same result. I think that can definitely increase confidence. But if you see things trending in a very specific direction, there's no guarantee that it's going to keep trending in that direction. It's going to stop, or it may go back the other way. And some work that Tom Hamill did on the global models showed that a lot of those trends are not very reliable predictors of future trends.
Okay. Second question has to do with the so-called poor man's ensemble and regular ensembles, and I'm curious if anybody's considered combining them into a so-called super ensemble, where you take regular ensembles like the hurry, combine that with the href, maybe see if, grab something that OU's running, the NCAR ensemble, put as much of those together as you can to make the href have even more members.
Yeah, that's not something we've tried yet. We've combined the hurry and the NCAR ensemble for part of the flash flood and intense rainfall experiment, but I haven't seen the results of that yet. Yeah, I think it's a good thought experiment, but in real time, realistically, you wouldn't have both of those systems running, just purely from a resource standpoint.
Okay, thank you.
I had a couple of questions for you, Trevor, too. One thing that was really interesting to me was the stochastic approach. There seems like there is such a huge number of things that you could perturb. How would you determine what would give you good spread?
Combination of guesswork and a lot of experiments. Yeah, they're really, you're absolutely right. There are so many things you could change in the model, and there seem to be the folks who work on those physics parameterizations seem to have very specific things that they're comfortable with perturbing, and very specific things that they're not. And I think we need to push those boundaries a little bit, just because the fact that we're not getting a big increase in spread means that we're not targeting the right areas yet, and we're not targeting them hard enough. So I'd say there's a lot of potential in stochastic physics that remains untapped.
Yeah, it seems like it seems really exciting. It seems like that's an area where you can really increase your spread in an intelligent way, far beyond what we're doing right now.
Yeah, absolutely.
The other question I had was on what do you think the impact, from a forecaster's view of the href, looking at the output when version 2.1 comes on, what's the impact for us in the field due to the bias correction? Is it going to be pretty noticeable, the quality improvement?
In the first few hours, yeah, I think so. Especially with higher thresholds, there's a pretty significant high bias in, say, 1 to 3 inches of rainfall in 6 hours. So that's an area where I think if you're going to see a pretty significant decrease in the probabilities, and it's going to be a correct decrease, because you have a combination of a high bias and not quite enough spread, and you're going to be doing bias correction and spatial filtering to correct that. But at longer lead times and in the cold season for lower thresholds, I don't think you're going to see a huge impact in the bias correction. But I do think this EAS variable radius filtering is going to make the probabilities a lot more useful.
Okay, yeah, that's exciting to see that the EAS stuff is being leveraged as well. And even if it's just in that short-term range as far as the bias correction goes, toning down the probabilities on the high-end amounts is definitely something valuable for sure. I don't think we have anybody else. I don't see any other hands raised. Last call for questions here while you got Trevor on the line.
Before anybody else chimes in, Trevor, I just really want to thank you for providing this talk. I've gotten to know you a bit better here in my new role over the last handful of months, and I know when you made presentation somewhat similar to what you just provided our SOOs here a month or so ago when I saw you in Boulder, there were some light bulbs that went off in my head, and as we talk about smart post-processing to enhance our ability to provide the best possible IDSS in a scientifically sound manner for all of our decision makers out there at local FOs, the connections are tremendous. So Randy and I were talking behind the scenes here that your talk here would just serve as a phenomenal foundation or some derivative of it for our field forecasters to begin to spin them up toward more probabilistic, more of a probabilistic mindset, and working with ensembles and really broadening their understanding of ensembles. As I think you and I talked before you started speaking, I think our average forecasters have a very basic, rudimentary, what ensembles were maybe 20 years ago, sort of a mindset. And I think there's so much more out there for them to understand, and it's critical for them to understand so that they can effectively leverage that and communicate it to our partners again. So not a question, just more of a comment to thank you for a great presentation, and we will certainly share the recording with our field offices so that they can pass that on to their forecasters as well.
Great, thanks, Bruce. And yeah, if there's maybe a future PowerPoint that's kind of leads people through this, I could certainly help put that together with you.
Oh, fantastic. We'll be in touch for sure.